Okay, so this week we're going to do moment inertia. So you log on to Canvas, click on menu activity and click on moment inertia. And let me bring up the file. So let me do this. All right, so what is the moment inertia? Moment inertia is equivalent to mass when an object is in rotation. So when you have an object that's moving, let's say you have an object in linear motion, then the mass of the object would just be mass. But when you have the object that is actually rotating, then instead of thinking of it as a mass, you have to consider how the object is rotating and about which axis that is rotating about. So then we have another quantity that is equivalent to mass, which we call that moment of inertia. And the moment inertia really depends on the mass distributions about the object and also the rotation axis. So in this lab, you will introduce two different objects and in three different rotation configuration, and you'll find that the theoretical value for the moment inertia are different. Um, we're just going to focus on rotations about the central mass of a disk. So this is the ring, but nevertheless, I'm just going to go over the stuff in this activity. So you have a ring, and the ring comes with two different radii. You have the inner radius R1, you have the outer radius R2. So if you follow the definition of moment of inertia, then you can actually estimate or calculate the theoretical value of rotational inertia, which is 1/2 mass of this ring, and then times the R1 squared plus the R2 squared. Okay, so this is when you have a ring rotating about the central mass, which is the axis through the center of the ring. And then another scenario is that you have a disk, and the disk has a mass m, and it's rotating about the center mass, which is this configuration. So when you have rotating about the central mass, then the theoretical value of rotation inertia is 1/2 mr squared, and r, of course, is the radius of the disk. However, if you using the same disk, but then it is rotating about the diameter, like the configurations on the right. So you'll see that when it's spinning around the rotation axis like this, then the rotation inertia is 1/4 mr squared. So you can see that even with the same mass, with the same disk, if this rotating about a different axis, then rotation inertia will be different. So on the left, it is 1/2 mr squared. On the right, it is 1/4 mr squared. So you can see that on the right, when it's rotating about the diameter, it is easier to rotate because the I value is smaller than the I value on the left. Okay, so in this experiment, the setup is like this. You will have so this is what we call the A base, and this one is the Fordham gauge, which we use to count the rotation per minute per second, so that we can estimate the angular velocity, and we can also estimate the angle or measure angular acceleration. So this one is what we call the vertical shift. And then horizontally, there's a horizontal pulley, and then we're going to have a thread that is going over the second pull. Actually, on this vertical shaft, there are three different diameter of the pulley. We're going to use the middle one, and then you have the thread that wrap around the middle one of this pulley on the vertical shaft, and then that thread is going to wrap around this pulley horizontally, and then there's on end you're going to put the mass holder and also the mass. So this mass on the string is going to provide tension, which you should be familiar with by now. So if you draw a free body diagram, you will see that uh, the forces, if you just take any point, then there's a tension in this. If you just take this, as an object, and then draw a free body diagram, then you will know that there's a tension that's upward and there's a gravity that's downward. And if this whole thing is allowed to spin, then there's a downward motion for the mass holder. So this whole thing is going to accelerate, and so you have the mg, which is the mass here, and then minus the tension, and that the whole thing is equal to ma. And so this is how you, based on the free body diagram. And so when this object, starts to rotate, and then it's going to have acceleration. So you're going to keep adding masses. You're going to keep adding mass to this mass holder, and then let it spin. Let it spin. So each time, it's going to measure tension. It's going to measure acceleration. It's going to measure angular acceleration. But then we know that angular acceleration and linear acceleration, they are related to each other. So once you have the alpha, which is the angular acceleration, you'll be able to deduce the linear acceleration A. So that's basically, for the experiment, you will have a configuration like this when it's spinning about a central mass. And then this configuration on the right is when you change the configuration. So the same disk is going to rotate about the diameter, and then the thing on the left is when you put the ring on the disk and then let it spin. So data analysis wise, you'll just be dealing with the a configuration like this when it is rotating about the center of mass. Okay, and so let's go back to the theory. So we know the experimental setup is like this. We know tension and mg and a, they are related, and there are additional equations that you also want to know. So for when we have the rotation about the central mass, we know that theoretically the rotation inertia is 1/2 mr squared. And so we know that the angular acceleration is alpha, and that is equal to a over r, linear acceleration over the radius. This little r is not the radius of the disk, it's actually the radius of the pullet, which when we go back to the second page, I'll show you that. And we also know that torque is equal to I alpha, right? So experimentally, we want to deduce what is the I value, and then we're going to compare to the theoretical value of 1/2 mr squared. M, of course, is the mass of the disk, and R is the radius of the disk. And then so experimentally, this is the equation we base on. So we need to figure out what is torque and what is alpha. And alpha is measured directly from the experiment. And then when you plot torque versus alpha, then the slope is going to give you the experimental value of rotational inertia. Okay. And so how do we get to the value of torque when alpha is directly measured? So we already know that alpha is directly measured, and also alpha is equal to a over r. So meaning that you can deduce the acceleration of the system is equal to alpha times r. Okay, and r is the radius of the pulley. Now, in addition to that, we know that just based on the free body diagram that mass the whole the mass on the string mg minus t. So that's if you remember the free body diagram, you have the mg here, and then there's a tension, and the whole thing is moving downward. So you have the mg minus tension, that's equal to ma. Rearrange this, then you get your tension, which is mass times g minus a. G, of course, is positive 9.8. And what is our a? A is actually obtained from this equation, alpha times r. So you have your tension value, okay? And once you have your tension value, Then if you remember, we also introduced that torque is equal to L, R cross F. So in this case, your R and F, which is T, are perpendicular to each other. So torque is R times T. So now, and the R here again is the radius of the pulley. So you have the torque, which is R times the T, and T is obtained by this, and your A is obtained by this. So once you have that, then you have everything in front of you to plot torque versus alpha, okay? And so the slope, so the slope is going to give you the experimental value of the experiment. In addition to that, we know that when we do this experiment, there's a lot of friction involved, and the frictional force can actually estimated by when you have the intercept, then the frictional force present in the experiment would just be the intercept, the y-intercept. This is the y-intercept, and then over the y-intercept over the radius of the pulley. Okay, so a common mistake that student will make is that instead of using the radius of the pulley, they are using the radius of the disc. One is capital R and one is the lowercase r. So the symbol are very important. You want to make sure that you keep track of which one stands for what. Okay. All right. So that's so the what is the radius of the pulley? The radius of the pulley um, refers to the middle on the vertical shaft. So this is the pulley. It comes with three different diameters. We're using the middle one, and you'll be provided the value, and then so you'll have that value. Okay. So let me see what else. Okay, and so the data table will look like this. So you'll be given the diameter of the pulley and calculate the radius of the pulley and convert it to meters. And the hanging mass, the mass of the mass of the mass holder will be given, and the mass of the disc will be given. The diameter of the disc will be given in centimeters, and you want to calculate the radius of the pulley and divide it by 2 to get the radius. I'm sorry. You want to use the diameter and then calculate the radius, and then convert it to meters, and then you can calculate the rotation inertia. About the center of mass. You don't have to calculate about the diameter. Okay. And the mass, so I think each time we're going to add, you're starting with the 50 and then adding 10 grams in each time. And remember that 50 gram will just be the 50 gram on the mass holder. So you need to include the mass of the mass holder as well. So it would not be just 50 50 grams, it will be 50 plus something. Okay. And then you have to convert it to kilogram because everything has to be in SI unit, and alpha will be given. And then based on the equation we just went over, you want to calculate the A, you want to calculate tension, and then you want to calculate torque. And once you have the torque, then you'll be able to plot torque versus alpha. And then from there, you can find the experimental value of rotation inertia, and then compared to the theoretical value to calculate percent error, you have the y-intercept, and then from there you can calculate estimate the frictional force. And then how do we deduce the frictional force? Basically, you can just look at this equation. So experimentally, this is the alpha is the one we measure. So experimental value of torque is I alpha, and then that is actually equal to, if there's if the friction is present, then the torque, ideal torque, and then I have to take into account the presence of the frictional force, and so minus frictional force times the radius of the pulley, because torque is equal to R cross F. So this is your RF here, and then so move around this, then you'll get your this is ideal torque, and that's equal to A alpha, which is what you measured, and then plus the term that you can that was inherently in the experiment. And so from there, you can estimate the frictional force present. Okay, so that's basically what you want to do. And let me show you the data so you know. So again, you have the data that's provided in the Excel file. You are welcome to just use that Excel file, download the data file from Canvas, and then just work from there. Use that as a template, and then filling and then calculate various quantities and things like that. And then I also wanted to actually organize your data. When you have the result like this, and then maybe you can skip this, and then have this, or you can have everything put in the Excel file. That will be fine. But you just have to remember that it's not just on the Excel file. It's not just the plot. You also need to show me these things as well. Okay, and so if you have if you include everything that you should have on this file in the Excel file, then you don't have to present this the data tables here. But if your data if the data in your Excel is not that well organized, then I would strongly suggest you have a data table shown like this. So it's easier for the reader to look at your experimental results. Okay. All right. So let me bring up the data. So the data, let me see, is the data table is look like this. So like I said, the radius of the poly is given, which is 2.485 centimeters. So based on that, you want to calculate the radius of the poly, and also it has to be in SI unit in meters. The mass holder has a mass that is 5.35 grams, and the mass of the disc is 1.44, and diameter of the disc is 22.83 centimeters. You want to calculate the radius of the disc in meters, and then calculate the theoretical value of the rotation inertia about the central mass. And then each time when you put some mass on the mass holder and we let it spin, the program is going to measure angular acceleration. So this is this is when you have the 50 grand, and then you also have to include this 5.35. So this you need to calculate. You need to calculate the total mass, which is 50 plus 5.35, and then remember to convert it to kilogram, and do that for the rest of the masses, adding to the holder. And then each time you'll get the rotation inertia. I'm sorry, the angular acceleration. So you're going to use the equation I just mentioned to calculate the linear acceleration, the tension, and also torque. So of course, you should be very familiar with how to use Excel to do various calculations. Do not key in those data to the calculator. Just use the Excel to do the calculation. Okay. And so for each quantity like A, T, and torque, and also CM, you want to show the simple calculation just for one value. Let's say you just use the show one example for 50 grand, 50 plus the 5.35. So your mass would be 55.35, and then use that to show you how you calculate your A, how you calculate your T, how you calculate your torque. And you want to plot torque versus alpha to get the slope. And then once you have that, then you want to remember to calculate frictional force and calculate the percent error and things like that. Okay, so that's basically what you want to do, and we'll just be using one set of data to do the calculation. Okay, alrighty.